In this part of the video, I'm going to be walking over the different parts of the power rail of our breadboard. The power rail are these horizontal metal strips that run across our breadboard. And I'm going to explain the different parts of it using a drawing, using a comparison, and then we're going to take a look at the board itself. After we understand the power rail, we'll find ways to make our circuits on our breadboard look more organized, look more clear, and they'll be easier for other people to follow. So let's get started with the drawing. So here I have one instance of those power rails drawn on my whiteboard. And what we have here, we have a positive terminal and we have a negative terminal. And like I said, these are horizontal metal strips that are all connected. So everyone in row 1, we can call it, and this is our positive terminal. Every single one of these has a metal strip behind it and it's connecting to get together. The same is true for the bottom row, row 2. And so what happens is, if I have a battery, here I have my Duracell battery, and if I connect it to this first insert on my breadboard, my entire line, my entire rail of row 1, they will be provided with that voltage value. For instance, if this was a 10 volts, now this hole is 10 volts, the second one is 10 volts, and this entire line is also 10 volts. So that's what the positive terminal can be used for. It can be used for that positive voltage coming out of my battery, whether it's 10 volts, whether it's 5 volts. And now if I'm going to go further more on my breadboard, I can connect a component out of that terminal and provide it with 5 volts by connecting it to any of the open spaces. And the same is true for our negative terminal. Our negative terminal can be our common, it can be our ground, and so this negative side of our battery can go to row 2. And so now every single one on here would be our common or our 0 volts on this bottom row. And that helps us stay organized in our circuit and connect the components to the end of our circuit if we're thinking about it being in a circle. Another way to describe this is, right here with me, I have a connect 4 board. If I was thinking of this red as my positive terminal and this yellow as my row 2 or my negative terminal, I see after I put in one red connect 4 piece, my entire row is also going to be red. So whether this is 5 volts or this is 7 volts or 6 volts, this entire row is going to have that same voltage value. So if I was to connect a resistor to this hole, it'd have 10 volts on the one side of it, or to this hole, it'd be 10 volts to one side of it. And the same is true as well with the bottom half, with this being ground or being common. Okay, now, so I'm going to model this on my breadboard. We did it on the drawing and we did the comparison, and now I can see what would it look like when I went to actually put in my resistors, put in my capacitors and my jumper wires to make a simple circuit. So here I can already see in my positive terminal, I have this red wire already going in, and we can say it's connected to my battery, the positive terminal of my battery. That is telling me that every single hole, every single connection on this line, horizontal line for the power rail, is all at that voltage. So let's say it's 10 volts, every single one of these is at 10 volts. And then my second wire, this black wire, I connected to the ground of my battery. So all of it is common, all of it's ground, all of it is going to be at 0 volts. And so now to model the circuit that's on the whiteboard, we have our voltage source and then we have our resistor. What I can do is I can take my resistor to my right hand. I can put it right into any one of these holes of the power rail. Okay. And then I'm going to end it off on this side right here. So what I've done is my power rail has 10 volts. That's my voltage source. And now I connected my resistor to this power rail. You can see it's connected to the red line. Okay. And the last step I need to do, I need to make sure the other end of my resistor is connected to ground. I'm going to look at it. Okay. Here. So let me connect it to the power rail of ground. And once again, it doesn't matter which hole I use, which connection I use on these, all of them are electrically the same. They're all electrically equal on the rail that it is on. So I can use whichever hole I choose to that makes the most sense for describing my circuit or for making it look clear and concise and organized. So now I can see my battery is connected to this positive red wire, this positive terminal. It goes to my resistor. My resistor ends here, and this is looped back to ground. I have a complete circuit. In this part of the video, we're going to be talking about the electrical contact strips of the breadboard. And the electrical contact strips of the breadboard is really where the magic happens and why it's so convenient for me to use instead of soldering something together. And that's how I can connect my resistor to my capacitor, my LED to my voltage source, or any component across each other. And those connections can be parallel connections, they can be series connections, they can be a combination of both, they can be a combination of neither, and it really helps me navigate making those more complex circuits. Before we get into making those complex circuits, let's talk about how it's labeled. So here I have a drawing of our breadboard. I have 10 of those contact strips, and so I have 5 up top, and then I have 5 below, and then it's separated in the gap in the middle. This resembles a breadboard in that horizontal fashion, holding it long ways. And there's a couple things on here indicated on our breadboards that tells us a little bit about it and gives us some more information. If you look at the end of that breadboard, we have A, B, C, D, E, and it goes all the way to J. And that is labeling those rows across my contact strips. And then if we look on top of our contact strips, we have numbers. They can be in increments of 3, increments of 5. The one I'm using has increments of 5. So it goes 1 to 5, but that also tells me 2, 3, 4. And that's telling me the column number. Those numbers and letters are important for if I'm given a schematic and they want me to represent it a certain way on the breadboard, or if I'm trying to communicate with someone, this is how I can represent it in a way that's concise and easy to follow. That's what those are used for. Those column numbers can be especially useful because everyone that shares the same column number is connected. Remember, for our breadboard, we do have these 5 inserts, but on our contact strips, these 5 inserts are all connected at the bottom with that sheet of metal. So this helps me think about my connections. If I'm looking at my circuit, am I thinking, are my 2 components connected at the beginning? Are they connected at the end? Is one connected to the end of another one? So those help me think about those. And let's start with this example circuit in the bottom right side. And all I have is a voltage source in parallel with 2 resistors. So I'm gonna start on the bottom half of my protoboard, or my breadboard. And I'm thinking about the nodes, I'm thinking about those connections they share. If I label this one R1 and R2, R1 and R2 are in parallel, and they should start in the same node, in that same connection. Okay, so why not I have them all start in column 2? So I can have one resistor right here, and then a second resistor right here, and they're sharing that part of it. If I go back to my circuit, I see they also end in the same area. Their connections, their end connections are connected. So this tells me they share a second node, also meaning that they're in parallel. So now I have multiple ways of representing this, but the main idea is, okay, I want my resistor to connect at the same end as well. And so now if I look at this, okay, so the beginning of each resistor is in column 2, and then the end of each resistor is in column 4. And if this is all connected and this is all connected, I know that I've set those up correctly in parallel. Okay, another way to represent that is, I'm still thinking about the same idea of them starting and ending at the same spot. I don't have to model it like this going all horizontal. Maybe that's not best suited for my purposes, or maybe it makes my board look a little too messy. So let me try another method. So if I'm just thinking about, okay, let's say I want to go column 1 to start off for this top node, and I want to go to column 3. Okay, so column 3, I'm going to use this top half now. Let me draw my inserts here. So I want to use column 1 and I want to use column 3. So I can just make my indicators. Let's say R1 starts here, R1 and R2 starts here. That's already a perfect start, okay? So if I want it to go 1 to 3, I can have my R1 go down here, R1, and draw my resistor across, and I can go my R2 go up here, R2, and it goes across. This is still the same setup, the same schematic as below. Even though it looks slightly different, it's just another way for me to connect my two resistors. And it's still equivalent because I'm starting at this same node and I'm ending at this same node. Okay, so now we have moved to our actual physical board. And let's explain those electrical contact strips again. So here's what I just did on the board, where we see, okay, in this case, we're starting on this column 39, and then we're ending at column 31. And I see they both start at the same position, and they both end at the same position. This is telling me that they are in parallel. I know that they are connected. And that's because those strips are lined up vertically in this case, on this side. So all of row 39 is connected, and all of row 31, or column 31 is connected. Another way of representing these parallel circuits, if I go to the other side here, it looks a little bit messier here, but this can be a good way depending on the circuit and my needs. So here, I see they're all connected on this row 59, and then I go across my gap, and the ends of the resistor connect on about 57. So it's the same circuit. I have two resistors in parallel here. I have two resistors in parallel here. And they're both representing the same thing. It's because I'm thinking of the connections of those contact strips, not what is actually being shown up top. And so this is how I showed how to do parallel. I can also show one example of a series connection. So if we're thinking about, okay, all I'm thinking about in a series connection, I want the end of my resistor to be the start of my second one. So let's just take this one out for right now, and we can look right here. For this resistor, I just have it going across. It's connected to row 41 and to row 39, okay? So if I'm thinking about a connection of one resistor here, and then I want it to continue on, all I need to make sure is, I need to make sure to have one shared connection. And that shared connection is going to be where this beginning of this second resistor connects with the first resistor. And that's going to be in that row 31. Okay, so that's perfect. Now where I end this connection of my second resistor, it doesn't matter in this case, but it would matter if I was to make a more complex circuit. It would matter if I was connecting it to ground. So if I wanted to connect it to ground up here and my power rail was connected, I could do that. Or if I wanted to connect it down here, because I had to connect it to something in my lower half of my board, I could also do that. But the main thing for this series combination, for this series connection, they have to share one node, they have to share one electrical contact strip.